All right. Yeah. Thanks, Frank. Hi, everyone. So so today we'll continue what we have been doing on Monday and Tuesday. So as promised, I don't see Raghavendra, but as promised, we'll start with some simulations. We'll show some pictures of what this model is supposed to behave in heterogeneity and also in ERGMs. And then in the later part, we'll show you some arguments of some paths which where the proof is quite robust, where the graph fission happens very quickly. So this is the plan for today. So we'll start with Shagarika, who will talk about the simulations, at least in the edition case, right? Yeah, Shagarika, go ahead.
Hello everyone, am I audible? Okay, so today I will start with some results based on Indrashrini that is already described the theoretical part by Elena on Monday's lecture. So with the brief introduction with the dynamics that we are following. So first we will start with an Indrashrini graph with n nodes and probability P that describes the probability of having an edge between any two vertices. And we have two opinions, and we evenly and independently uniformly distributed the opinions over the vertices. So this is the initial network we are taking, and at each time step t, we are randomly pick disagreeing edges. What disagreeing edges means, this is basically edge between two vertices, those vertices having the completely different opinions from each other. So after randomly picking the disagreeing edges with probability beta by n, we perform the voter model step. Voter model step basically shows we will choose randomly any of the vertices, and that root vertex will adopt the opinion of the other vertex. So with probability 1 minus beta by n, we will perform rewiring step. That means we will broke that disagreeing edge and choose any of the vertices, and we will connect that edge to randomly chosen node here. So the process will stop when there is no existing disagreeing edges. We call it the stopping time or absorption time. So this is the result for Indrashrini network. So if we concentrate on this portion, that for very less small value of beta, the absorption time is, we reach to the absorption time is quite faster. Like with also we have, so along this axis, we have plotted the minority fraction, with this axis the beta, and with this axis we have plotted the absorption time. So with less value, smaller value of beta, we are getting the minority fraction around 0.45, and this reaches respectively very much faster in time. That means we started with a network with randomly distributed opinions, but very fast these two forms two clusters with completely different opinions.
One axis is the minority proportion.
Minority fraction, along with beta, this is the minority fraction. At what the absorption time we are getting, right? We are plotting for each beta the absorption time at the end of the where there is no disagreeing edges, the number of fraction we are getting. Yes, this is the final absorption minority fraction. The left hand side is the absorption time, the when we are getting that. So for smaller beta, the absorption time is very fast, and for the large beta, the absorption time is we are getting quite late. So for in this region, we are getting very less fraction of minority opinion, and we are having this for higher absorption time. So we started with a network with randomly distributed opinion, but we end up with this phenomena that the entire network merges to only one opinion and leaving with a little bit minority fraction left. So here we are plotting minority fraction along this axis and the time steps. And from this graph also we can see the minority fraction stays around 0.45 and 0.5. So this is for beta equal to 0.2, which is small. And this is the discordant edges, disagreeing edges over the time step. And we get from this that disagreeing edges are continuously decreasing as we are reaching to the absorption state. So this is also for beta equal to 7, which is quite large value of beta. And we are getting the minority fraction going down. This is almost near 0.10, which is quite less than this. And we are getting discordant edges reaches to 0 with some large time step. And this is for beta equal to 7. So here are some results for sparse graph also. Sparse graph means we are allowing very little connections between the vertices. So the results are well established in Duret's paper. So for beta equal to 0.2, we are getting the, we have plotted the absorption time in this along this axis. And we have plotted the nodes, number of nodes we are taking. So this is almost proportional to n, that is almost linear. So
can
for
you define sparse, just to be clear, I mean the degrees are order 1.
Sparse means we are allowing the p is very much small. We have n vertices and we are allowing very much less number of connections there.
How much less in this simulation?
This is c equal to 3, c by n, the probability p, c by n. So c is, yes. So here alpha, this is, we can observe that alpha is tends to almost 2, near about 2. So the absorption time is quite, this alpha is 2 proportional to n. And for small beta value, the rewiring step is dominates here more rather than the voter model step. So the graph splits into cluster very fast, as we can see here, the minority fraction, all that I described before also. Minority fraction is almost near between 0.45 to 0.5, and discordant edges also shows the fast absorption state. And for large beta, the voter model step, the voter step dominates, and we get the minority shrinks towards very less fraction like 0.10 here. And for this is beta equal to 0.7. So this shows that we need much time to reach our absorption time, that there is no disagreeing edges left. So these are the results that is for ER graph. And I will hand it over to Karan for ERGM.
I have a question. So your simulations here, do they give you a rough value of what the critical value should be?
Beta?
Yeah, of beta.
We can show this.
So it's somewhere between 0.1 and 0.7, but do the results give you something sharper already or not?
Not exactly we got that, but we can think of there, it will be somewhere 0.3 or near somewhere there.
Great.
We can.
Can calculate just to add on to this. I mean, we can calculate beta critical. I mean, depending on the size of network. But
it will depend upon the size of network.
We do have the sort of half
Yes.
minority. So yeah. So thank you very much. So I'll be continuing with the same sort of results in the ERGM, right? So, yeah. So I mean, we have seen the results on the ER dense graph, right? So what we believe we sort of get the similar results in the in this ERGM model, right? I mean, we'll see. So this is our model. This is our probability distribution, right? So which is already Elena described in his first lecture, right? So here we have this a number of edges term, which is EG, and then we have number of triangles, that is delta G, right? And up to with this scaling, I mean 2 for the number of edges, and then x is by n for the triangular densities, right? So yeah, so what we believe in some parameter regime of this beta 1, beta 2, right? I mean, if you are in that dense regime of, I mean, Ardor-Shiny graph, so then maybe we can, I mean, so in that thing, I mean, this ergum behaves as a, I mean,
Yeah, Argam was a dense Erdős-Cheney graph where it's like P we can replace by U star, where U star is the maximizer of that rate function, which Alina shows in the first, his lecture, right? Yeah, so so there are two things, in the, it's not straightforward as the ER graph. So first we need to, sort of generate this ER graph, ERGM, right? So yeah, so first I'm going to sort of show the flow of the generation of the ERGM graph, right? And then we'll see the result on top of it. Right. So what do? We can start with any sort of a, template, right? Template graph. We can start with the Erdős-Cheney. We can even start with the empty graph, or you can even start with the complete graph, right? As long as you are just subjecting it to the good enough burning period, right? Burning period. Just at that sort of, it will converge to the ERGM target distribution, right? Yeah, so this will serve as our initial configuration. Then we'll define our ERGM parameters, which is already described. Beta 1 is the H term, beta 2 is the triangle densities, and this is the target. This is our targeted sort of distribution which we want to hit, right? So yeah, so now what do? We cannot, you can see, in this model, right? Argam model basically, this is not normalized. So, the normalization concept is not easy to calculate. There's very compute, there are too much compute in that thing, right? Because just the number of graphs, sort of there are exponentially many graphs.
Sorry, I have a question. So this exponential, you should multiply it by the probability of the Erdős-Cheney graph itself, right? Because so the Erdős-Cheney random graph is your reference graph, and now you bias it with this vector.
We start with the Erdős-Cheney graph, right? And then with this probability, I'm going to show like which probability we're going to use, and then we're going to rewire the edges just to hit this distribution. It will be clear in some moment, right? Yeah, so of course, as I was saying, that normalizing constant, is very hard to compute, so we have to find a workaround just to do that, right? So what we're going to do is something called Gibbs update, right? So in this thing, yeah, we're going to select the random number of, we're going to select a pair of node UV, right? And then we compute their number of common neighbors, right? And then we can compute the edge probability, right? And this is our sort of, I'll explain this thing in a later slide, and then we'll calculate this, change in the energy, which is twice of beta 1 and sigma and beta 2 times the common number of neighbors, right? And then this will convert this thing into the probability, sort of, which is a logistic function, right? E delta minus H. And then with this probability, we're going to remove the edge or add edge in this initial configuration, right? And we'll subject it to the, good enough number of, burn-in period, and then we can achieve this sort of a Argam distribution, right? I'm going to explain like how do you calculate this probability in the next slide, right? And then once we have this probability, we're going to add the edge UV, and then otherwise we'll remove it, right? And then we'll repeat this in good amount of time, and then maybe this initial sort of your starting graph will, hit the, the sort of targeted distribution, right? So this is the, then the graph would be sampled from this distribution, right? And again, just to reiterate, the Sagari already sort of mentioned this thing. So this is our dynamics, just to reiterate, right? So this is our probability beta n, which is the voter step, and then 1 minus beta n, the remaining probability is basically the uniform rewiring, we are doing it, right? And now again, when we are doing this uniform rewiring, right, we are not subjecting it to sort of follow the Argam Gibbs, right? Once we have the Argam, graph, right? But once we have Argam, we are not going to change it, with the dynamics, right? We're not going to force it. We're not going to enforce it at every step when we are rewiring, when we are doing this rewiring dynamics, right? It just once we have the ERGM, and then we'll just let the dynamics play. We're not enforcing at every step that it should follow the Argam distribution, right? So that is very critical. Yes, so this is, again, just to mention, right? We just, whatever we are plotting, the result we are plotting against beta, not beta by n on the x-axis, right? So it's a beta, right? If you say beta more than 1, so don't just sort of scratch your heads, right? Yeah, so then that edge probability we were discussing in the last slide. So how do you calculate that Gibbs update, basically, right? So, yeah, so edge could be in two possible states, right? So let's say if a graph has an edge, so we call it 1, and 0 if it does not have an edge, right? And then, yeah, and what we want to choose between these two states according to the Argam distribution, right? So now, and then we'll compare the probability of these two graphs, right? Let's say G1 is our graph which has this edge, and G0 is the graph which without the edge, right? And then what we do, we already know our distribution, which is exponential, right? Then we can write their individual probabilities. And this is a change in, this is the Hamiltonian basically, which we have. And then what we're gonna do, we're gonna write their proportional corresponding probabilities, and then we going to take the, and we're going to define the conditional probability, right? So the probability of a graph has an edge that is x mu nu is equal to 1 given the rest of the graph, so that is proportional to this. Right? By doing so, you can see we are canceling the numerator and denominator, the normalizing cancel, right? So this is a very common trick which people use just to create the algorithm. Right? And then how do you calculate this delta h? Because right, we have the delta h in our that logistic graph. So this delta h can be, which is the difference between these two Hamiltonians, right? And then, yeah, so just sort of rearranging this thing, dividing and, dividing numerator and denominator by e power ehg1, then you can sort of write it in this neat form, which is the logistic function in delta h, right? Now, how do you calculate this, the change in Hamiltonian, right? So when we add h, right, we increase the h density by 1, and when we add a triangle, right, the number of triangles will increase by their common number of neighbors, right? So yeah, so up to the scaling, your delta h will become this, right? So yeah, and then you define the probability, and with this probability, basically, you will just rewire your edges from starting from the Erdős graph or the empty graph, and then with this probability, you just add an edge or remove an edge. So and do it in enough number of time, and then you will get your desired outcome distribution, right? So what does it mean, basically, this delta h? If delta h is, if delta h is large positive, right, then your probability is 1, which means the edge will almost be present in that graph, right? If it is negative, then there's very less probability that it will be there in the graph, and if it is in between, so basically, so yeah, so it's half probability it will be there or not. Right, so we'll do this thing, good enough from time, and then eventually we'll reach the algorithm, right? So now we know the construction of the algorithm graph. Now we do have the ERGM at our Discord. Now what we're going to do, we're going to sort of run the similar results which we have in the dense Erdős graph, and then we'll see if we get some sort of a parallel between these two, right? So again, the same thing we've seen in the small beta case, right, in the dense ER graph. So basically, in which small beta means, because since the beta is the water strength, right, small beta means the rewiring dominates there, and if the rewiring dominates, we know, right, so there is not enough time for graph to sort of reach the consensus, right? So it will reach the consensus by splitting into 2, which your minority will remain, there are 2 sort of cluster which she has already shown in the ER graph, right? So the minority sort of, fluctuate between 0.5, right? So they are sort of 2 equal. There could be more also, right? There are 2 clusters, right? So we sort of have the rewiring dominance in that case. And then this rewiring sort of takes n squared time, right? Because we have n squared edges, so it will take n squared time. So you can see this sort of scales as n squared in the absorption time. And on the other hand, we have this large beta, which is mean water dominance, right? Because beta is our water strength. So if you have large beta, so basically, so their rewiring doesn't work. So beta, so there we don't, in that thing, the sort of consensus is eventually reached, but right, the cost you have to pay takes more amount of time because it will take n cube sort of a step, right? We'll explain why this is n cube, right? So you see, you start with 0.5, and then sort of, this is not done for the, I think, it's not done for the large enough beta. So the trend you can see from the trend you can tell, right? It started from 0.5, but it's going towards decreasing trend, right? So if you do it for the large enough beta, right, it will just go to 0. We're going to show you at the end of this thing. It does go to 0, right? Unlike this case, you see, it just sort of comes. It's not coming down. It's almost around 0.5, right? And in this case, it will take more amount of time. It will take n cube steps as opposed to the n square steps in the dividing one, right? Anyways, so yeah. So now what we are plotting here, we're plotting the same sort of thing. We are plotting the minority fraction here versus this beta water model strength, and on the right-hand axis, we have the time by n squared normalized. Right, so now this, again, the same thing, right? As beta increases, we do expect the minority should come down, right? And if beta tends to infinity for the, infinite, if beta tend to infinity, right, for the infinite graph, like it just, the minority should diminish, it should go to 0. And then we have this sort of increasing absorption time, right? For the small beta case, right, where the rewiring dominates, right, it takes n squared amount of time. So you can see, is sort of straight, sort of flat in the n square region. And then when you go to the large beta case, so there you have water model dominance. So water model will take, n cube steps. So there you can see, it takes more, it takes sort of n cube in the n squared normalized axis, right? So yeah, so this is sort of the same behavior we are getting. Yeah.
So each dot here is based on how many simulations?
So each, no, this is done for 5 runs. I mean, we should,
Each dot is the average of 5 runs.
5, yeah, we should be doing it for more. I mean, just to,
N, how large?
and in this case, I think it's 100. I mean, it's, yeah,
N equals 100.
yes.
You still have to
We,
grapple with a lot of fluctuations.
yes, I mean, because I mean, in this small n thing, right, you do have a finite size effect. So, I mean, we are trying to get the, I mean, result for the more, I mean, the larger one. We'll see the update on the Monday for that, right? And now the scaling part, right, as we have seen, right, for the small beta case, we are in the rewiring dominant regime, right? And then in that rewiring thing, right, it has, there are n squared discordant edges to remove. So it takes n squared amount of time. So you can see in the, I mean, if you plot the absorption time by n squared normalized, it should be flat in that thing. So you can see it's almost flat in that region, right? So it scales n squared with the system size. Whereas in the other end of the beta, right, in the large beta regime, so basically this water dominance, right? So in water dominance, it should be the graph should sort of remains flat in the n cube normalized absorption time scale, right? So this is not sort of flat, I mean, in this case, because I believe this is not done for the large system size. We are starting from 40 to 100. I mean, if you start from 100 and go for the good enough, I mean, larger value, we do expect the sort of flat in that thing, right? Yeah, so finally, which I promised, right? So we are plotting the minority fraction versus this beta for the, this is, I think, done for the system size 50. So now when you hit the 50, right, your minority will diminish to 0, right? So this is your, basically, when it's like complete water model, classical water model, right? So it will take n cube steps just to go to there, right? Because, I mean, if you, from the duality intuition, right, you have n walkers, right? And then it will take n squared amount of steps to meet, right? And then the total coalescing time would be n cube. So this is what we have shown here. Yes, now, I mean, then there's this beta 1, beta 2, you can choose, right? They'll be updating you on the Mondays, like, you have to choose very carefully this beta 1, beta 2 regime, otherwise you will be in some, that dangerous zone, right? Which we have already shown in the first one, right? So there should be some method to choose beta 1, beta 2, right? So that you are always, your ergom always falls in the dense ER regime, right? That G and U stuff, right? We'll be updating that thing on Monday. Now, if you have any question, I will happy to take it. Otherwise, my colleague, Deepening and Max will be continuing.
When you initialize the graph, you use the ergom to initialize.
No, we initialize with the Erdős graph, and then we'll do the burn-in period to create the ergom.
So yeah, so you run the, okay. I mean, I'm talking about this model. When you initialize, you take the exponential random graph.
Yeah, we sample it from the distribution.
Chosen at random.
What is uniform?
Color, the opinions.
Yes, that is IID, but only half of up. Yeah, that is, yeah. That is true.
Not related to the underlying graph.
And
point of initialization.
No, that does not, I mean.
So it's a preliminary conclusion that you say, if you look at your simulations, and of course they are not for extremely large yet, and
Yes.
you have to do, it's difficult to first generate the exponential random graph and then do the dynamics, et cetera, et cetera. But it does seem that in the ERGM model, things are a little different.
Yes.
In the sense that for very small and very large beta, it's similar, but somehow in the middle, you may be getting different kind of behavior.
Yes.
Do the simulations sort of
Yeah.
really hint at that?
Yeah, yesterday we discussed, right? I mean, so the thing is, I was not taking care of the scaling part, and that term I showed you, right? So I've corrected it, and then I realized the simulation just worked well. I mean, that the sort of this scaling part was there, right? In the model, you scale your edges by 2 factor, and then you rescale your edges, I mean, the triangles by 6 by n, right? So if you don't do this thing, then you will end up into the complete graph regime or either the empty graph. So this I was not doing, I mean, until sort of.
Yeah, but you might sort of first think, okay, you're tilting things a little bit and it doesn't really matter so much. You change the local structure and you should have more or less the same behavior. But your simulations seem to indicate that that's not the case. That somehow really doing this biasing will change a number of things dramatically.
I mean,
that's what they seem to say. Otherwise, you would not have these non-monotonicity things which are clearly there. I mean, they're not numerical artifact.
Yeah, yes or no. I mean, because this is again, I mean, we really don't know, I mean, what is exactly going on in that regime, basically, right? How we are choosing this, I mean, the numbers, because there are other schemes also where you choose this scaling factors differently, right? Then you sort of behave it differently. Like if you don't choose it at all, I mean, yesterday I discussed with you, just go to the complete graph region. Right?
Yeah, because this would make
Those we still need
the
to see,
project
I mean,
more interesting.
yeah, we still need to see, I mean, how robust this sort of model,
Yeah.
it's depending on the scaling.
It'd be good to have error bars around these points.
Yes, definitely we'll do it, I mean,
How much should impact the ED?
yeah,
Right.
it should be done.
Okay, thank you.
And all
Normal,
of
the, no.
some you've shown
So this is what we are trying to, I mean, show basically. So, I mean, if you choose this beta 1, beta 2 such that, I mean, your edge density that U star, right, is basically lies in that regime. Basically, it will fall into that ER, I mean, intense.
it's a simulation. I'm asking how does this all I do auto slide? How will these graphs compare? Similar?
Yeah, they are similar. Yeah. So
Because the graph remains there.
yeah, it's because the graph remains dense. I mean, so it's sort of at that I mean, burn-in period, right? So it behaves as a Erdős dense graph. That is what we are trying to show one-to-one correlation.
Okay, so as Sagarika and Karan showed you in this simulation that for small beta case, the rewiring step dominates, and in order of n square time, you reach the absorbing state. So we will prove this result rigorously, or we'll give you a brief sketch. Okay, so start with the initial graph G0, it's a random graph, and you have a Bernoulli opinion red or blue or 0 or 1 with for each vertex, and you perform this dynamics with probability beta by n, you take a Botar model step, and probability 1 minus beta by n, you take a rewiring step. And let xt be the number of disagreeing edges at time t, and tau be the first time where xt is 0, that is the consensus time, and let n star t is the number of vertices which hold minority opinion at time t. Then the result is, so let G0 be such that the maximum degree is linear in n, and the initial number of disagreeing edges is less than equals to n square by 2. So if G0 satisfies this condition, then for small beta, so there exists beta naught small such that for all beta less than beta naught, and for any eta bigger than 0, the consensus time is order of n square, and the minority opinion at time tau is close to half as n tends to infinity. So the proof of Basu and Sly is very robust in the sense that as long as their initial graph satisfies these two conditions, the same result is true, same result still holds. Dmax is linear in n, it's order of n. Okay. So we will give a brief proof idea. So let's define the stopping time. So tau 1 is the first time where the Dmax at time t, largest degree of the graph gt, is bigger than equals to 8n. And let tau 2 be the first time where your minority opinion at time t is less than equals to n by 3. And let tau naught is tau minimum, tau 1 minimum, tau 2. So the main goal is to give bounds for these three mixing times, and from the bounds the theorem will follow. So we'll show that tau naught is less than equals to 6n square, and both tau 1 and tau 2 is bigger than 6n square. So then the theorem will follow from these three estimates. Okay, so yeah.
If we max, how can the max degree be bigger than?
So it is at time t. So you are doing rewiring, you can end up with multiple edges. So it can be at time t. Yeah. So the first lemma is there exists beta naught small such that for all beta less than beta naught, the tau n is less than equals to 6n squared. And this will be done. So observe that xt is the number of disagreeing edges at time t. So if you perform a voter model step, what can happen is, so you pick an disagreeing edge. Suppose this is red, this is blue, and suppose this has also red, and this has multiple edges. So if I perform the voter model step, this is the root, and this vertex copies the opinion of this vertex, then this becomes blue, and so number of disagreeing edges can increase, right? And it can increase by at max d max t. So this is the term. So we are bounding expectation x to the power t plus 1 by n given ft. So this part is for the voter model step. And for the rewiring step, what can happen is that it is red, it is blue. Suppose this you remove this edge and again you connect with a blue vertex, then number of disagreeing edges remain same. So this is the first part, 1, and then it can happen that number of disagreeing edges can decrease. So suppose this is red and this is blue, you remove that edge and you connect with a same vertex, right? So observe that this is the n star t minus 1 by n minus 1. This is the probability that you choose a minority vertex. So you choose a minority vertex and connect to it, but there is then number of disagreeing edges will decrease. But there is a case that the root is majority. So we have to, then you, if it is majority and if it is minority, then again the number of disagreeing edges remains same. So there is a -1 here for that. And now you have that this expression, and from and on the, so if lambda is small and beta is small, on the event tau t less than tau naught, so you have bound on this n star t, and combining the bounds, you obtain this type of supermartingale type of expression. And since x naught less than equals to n square by 2, you consider the probability that tau naught is bigger than t, condition on the information. So this is bounded by this expectation, and you bound this expectation by iterating this result by t steps, so that you will get e to the power lambda x naught over n times 1 minus lambda by 10n to the power t. And since the x naught less than equals to n square by 2, you will get e to the power lambda by lambda n by 2, and this is lambda t by 10. And then choose t equal to 6n square, so that this probability tends to 0. Now Max will tell you the proof of lemma 2 and 3.
Okay, so I'll continue in the last 10 minutes with completing this proof. So what we have now, we know that the minimum over those 3 stopping times is of the order we want to obtain. And now well, the rest is to say that this minimum is in fact attained at the absorption time, right? So the first result will be that the tau1, which controls the maximum degree, is bigger than that threshold with high probability. So this is lemma 2. And I will also try to give you a rough proof idea of that. So what we need to do is we need to control the number of times that we rewire to a certain vertex, because this will increase the degree. And if that happens too often to a very particular vertex, then the maximum degree will increase. So therefore what we do, okay, as before, we sample our disagreeing edge. We sample the root of that rewiring. We sample whether we want to perform a rewiring move or not. If we do a Volta model move, that's all good. We will continue as we know. But if we decide to perform a rewiring step, this is how we find rewiring step means we sample a root from those 2 vertices in the edge that we've already sampled. And then the way we are going to decide on what vertex to rewire to is the following. So we define uniform distributed random variables on the number of edges. And then for the i's rewiring move, okay, we define Li, which is the first time, okay, we initialize at 0, but then the first time bigger than Li minus 1, such that we don't sample the root of the rewiring move itself, because we can't have self loops, right? So here's what happens. Okay, this is WLI minus 1. These are the samples that I've used up for my previous rewiring moves. And then I start at WLI minus 1 plus 1. I check, okay, is this VI? If it is, okay, we'll go on till eventually it is not. And if it's not, this is a valid rewiring move for our model. So we will add 1 to that bond. So in case that edge is already there, we'll create a multi-edge. If it's not there, we'll just add that edge. Okay, so a few observations on that. So obviously, the time in between, or the number of tries I have to take to observe not the root is obviously geometrically distributed with parameter n minus 1 over n, right? Because with probability 1 over n, I sample again the root, and with the opposite probability, I don't. So this probability I can control. So up till the 6n squared rewiring step, that I need more than 13 halves n squared tries samples of those random variables, I can control that it's smaller than that with high probability. Okay, so now what we will do is we will define the following auxiliary random variable, which is for a given vertex, the number of times in my WIs that I've actually sampled that vertex. So worst case scenario is, in our term now, is that every time I sample that vertex is not the root of the rewiring move, right? So this could be the number of times I increase the degree of vertex V. And then, okay, this is just binomially distributed with parameter 1 over n, and I try it 13n squared halves times. Okay, this can also be controlled by a Chernoff bound, right? So the probability that this for a given vertex is bigger than 7n goes to 0 exponentially fast, which is good because, okay, why 7n? 7n is good because we want to control the maximum degree being smaller than 8n. And then, okay, I add at most 7n vertices to the degree. I start with, this is one condition we have, I start with less than n because the maximum degree is less than n. So by union bound, I get that the probability that the maximum degree is smaller than 6n squared. The first time I observe a degree higher than 8n is small. Of course, on the event that I sample less than 13n squared times, but that probability is also small. So overall, we've seen that, okay, the maximum degree is not the time, with high probability, not the time where that minimum is attained, that tau 0. So last thing we need to control now is the probability, okay, that this minimum is not attained by the minority fraction stopping time. So the statement is, okay, here we need some assumption on the beta. So there exists a beta 0, possibly small, such that for all beta smaller than that, the probability that that tau 2 is bigger than 6n squared minimum tau, which is the absorption time, is high. So with high probability, that minimum is attained there. It's not attained there, sorry. Okay, rough proof idea of that lemma. Okay, we know that the number of Volta model steps up to time t is binomially distributed with parameter t and beta over n, because it's the probability with which we choose a Volta model step, and this is what we want to control now, right? Because this is on the tau 2 is on the minority fraction, the minority opinion. So we need to control the number of times I can have changed that. With the rewiring move, I won't ever change the minority opinion, but with Volta model steps, I can. Okay, so on second observation is that on the event that t is smaller than tau, the difference between n0 of t and 0 of 0 performs a random walk on the number of times that I've actually chosen a Volta model step, right? So I either decrease by 1 or I increase by 1. Okay, and then we will use those two observations, again, the binomial distribution and the random walk observation, that we want to condition on the fact that we initialize somewhere centered, so we don't have a minority fraction that is too small in the beginning, which we can do, which we can control. So this goes to 0. Then, okay, by the fact that this is binomially distributed, we can control also the number of voter model steps up to times 6n squared being bigger than 12 beta n. And then lastly, what we need to control is, okay, the probability that this random walk exceeds that interval that we want to stay in. So the first condition is that our initialized random walk, right? If we start n0 of 0 somewhere, that it is in that regime here, 2/5 and 3/5 times n. So there this is this condition that we are bigger than this. And then the second condition is just that, okay, we don't take too many steps in our random walk, essentially. And then, okay, if we choose beta small enough, we can just choose it so small that we don't take enough steps, right, to be able to move to n over 15. So in that sense, this probability is 0 if beta is chosen to be small enough. This now completes the proof idea of the lemma, of the third lemma. So overall, what we've done is we have bounded the probability. We've bounded the minimum of those stopping times, and then we said, okay, the minimum is not observed at tau 1, the minimum is not observed at tau 2. So with high probability, so this is a high probability event, right? That tau 0 is smaller than 6n squared, but the other ones are bigger than 6n squared, or at least bigger than tau. So with high probability, our absorption time is smaller than or equal to 6n squared, which is exactly what we wanted to see or observe for the first probability in that proof. And then the second probability is on the minority fraction being close to 1/2. And this essentially follows by the same random walk estimate that we've just seen in the proof of lemma 3. Okay, so quick summary. The takeaway is the proof in the small beta case works for a very big class of initial graph, essentially every simple graph, right? Because we only require that the maximum degree is smaller than 8n. So if you don't have a multi-graph, it will work. So it includes a huge class of initial graphs, especially the exponential random graph, which is sort of the starting point of our project. So the part where we will need to put in work is the voter model, the big beta case where the voter model takes over, sort of. So the whole duality comes into play, and then the geometry of the graph will come into play. And with that, thank you for your attention.